Good afternoon, everyone. We're going to get started here. I want to put a little disclaimer on today. I'm like completely exhausted today. I've been up since 3:30 in the morning, so I'm a bit delirious right now. So watch my math for little like stupid mistakes. Just I've already made a couple today. So all right, so we are going to have a test on Thursday. I sent out 3 old exams for you to look at. So were there any questions or concerns about the test? Anything you want to talk about? I guess you're okay. All right. Maybe there will be an opportunity at the end of class to answer any questions. If not, visit me during office hours. Today, we're going to just do one more optimization problem from 4.5, and then we're going to start 4.7 antiderivatives. Again, this will not be on the test. Antiderivatives will not be on the test. So, that doesn't mean tune out, but just be aware you can always go back and watch this, because I'm sure you're trying to cram all the other stuff in for the test. So, all right, let's get going. So I had this problem sitting here. A right circular cylinder is inscribed in a cone with height of 2 feet and a radius of 3 feet. Find the largest volume of such a cylinder. Now, I wanted to give you a problem like this because these are kind of like classic optimization problems. And classic in the sense that I know when I saw them for the first time, I'm like, what in the world are you talking about here? Like, this is weird. Inscribing something in something else. What does it mean to inscribe something? So I wanted to do this so that you would have some idea of what the terminology means here. So we have a cone that has a fixed height and a fixed radius. So I'm going to draw that first. I'm going to draw it in red. I have a cone. We all need to know what a cone looks like 3-dimensionally. Right, that's my cone. And what I've been given, and this is not drawn to scale, this is 2 feet tall, and the radius is actually 3 feet. So it should actually be more like this. Maybe I should have drawn that.
Professor, the question says cylinder. I don't know if that part is wrong.
Well, okay, we're gonna place a cylinder into a cone.
Okay, I get it now.
And so the cone has dimensions that are fixed. All right, so I'm going to start by drawing the cone, and yeah, I'm redrawing it because I want it to kind of match the wording there. We have a cone that is 2 feet tall and has a radius, so the distance halfway across is 3 feet. It looks a little bit more like it. Now, what we're going to do is inscribe a right cylinder into it. Now, a right circular cylinder is just like a soda can. We want to put a soda can inside of this thing so that it is inscribed. So what that means is when I put the can in here, I'm going to do the can in green. This is not okay. That's a little can sitting in here. That is not what it means to inscribe. To inscribe means that the top of the can must touch the top edge of somewhere on the cylinder, somewhere on the cone, and then the bottom of the cylinder would then touch the bottom of the cone. So that would be one possibility. Another possibility, let me draw you another one. I could do a really, really wide cylinder, right? Like this. And in that case, right, that cylinder would be wider, but it wouldn't be as tall, right? And I could get real crazy with this. I could go really, really wide, right? But then I'd be very short, right? And let me do one more. I could go really, really narrow, right? But it would be really, really tall. So there's all these like infinite possibilities. Ash, do you have a question?
Yeah, does it have to be like does the base have to match the base in that sense? Like can it be like on its side when you say
No,
inscribed?
when we say inscribed, the base of the cylinder must be flat with the base of the cone. And the
Got it.
top edge of the cylinder should, as you're drawing the cylinder coming up, when you hit the cone, you have to stop. So you don't want to come out of the cone and you don't want to be below the cone. You want to just touch the cone. So like
Got
if
it.
you looked at this from the top, right? If you looked at it from the top, you would see like the cone would look like that, right? From the
Yeah.
top.
Yes.
And so what you want is that, you know, let me just do the green one. This green edge here, that's this top edge right there, right?
Right.
Must be touching the cone, right?
Yes.
And then, you know, you have every variation in between. You could go from like a single point straight down. Now that wouldn't be a cylinder, but that would be like one extreme. It's like a single point. And then you could go all the way out, but if you go all the way out, then you won't have any height to it. So the question here is to, since we've got a fixed cone, right? The cone's not changing. We want to find the largest volume that we possibly can for the cylinder that we put in there. So all of these cylinders that I've drawn here have different volumes. They will not have the same volume. We want to figure out which one will give us the most volume, the biggest volume. Does that make sense, everyone? So let's do the optimization. All right, the first thing we want to do is figure out what our objective is. So the objective here is to find the maximum volume for the cylinder, right? So what I need in order to find the maximum volume of the cylinder is to kind of go and look at what the volume of any cylinder is, right? So we have a formula, we talked about this before. The volume of a cylinder is pi r squared times h. That's the volume of a cylinder. Now I have all these cylinders drawn. I'm going to erase some of them. I hope you're okay with that. I don't want to have to redraw the whole damn thing. Okay, so I had this right here. That should be enough to, so let's just look at that one right there, the green one. So that's an arbitrary cylinder. I'm not going to fix any of the dimensions. So I'm going to call the height of this thing h, right? And then the radius of this cylinder, I'm going to call it r because it's arbitrary. I don't know what it is. If I change r, h is going to change. If I change h, r is going to change. So they're variables, right? So I want to find the maximum volume for the cylinder. And now I've assigned variables here. And so I'm trying to find the biggest V can become. But right now, V depends on two things, right? R and H. There's two variables there. In order to do optimization, we have to get it to a single variable so that we can do the calculus. So now we want to think about, do we have a constraint? So are there any constraints we have here? Well, we know that the cylinder has to be inscribed in the cone. So it can't just be as big as we want it, right? And if I fix a height, then the radius is determined, right? Like if I tell you, hey, draw me a cylinder, go up 6 inches, then the radius is going to be fixed, right? It depends on that h. But we need to find the relationship between the r and the h. We're going to try and find some connection between r and h. So what we'll do is something we did back in the related rate section. You remember when we had that problem when we were filling up a cone with water and we cut the cone in half and opened it up and looked at it from like a cross section? We're going to do the same thing here. We're gonna cut this down the middle. And if we cut it down the middle and open it up, it won't look like the cone anymore. It'll look like a triangle like this. And then inside of the triangle where the cylinder was, would be the shape, the shape would be a rectangle like that. So this is a cross section. Now, the reason I'm drawing a cross section is because I'm hoping that the cross section will help me create a relationship between R and H, some equation between R and H. Then I can solve for R or solve for H and plug it back into the objective. So let me label some things here. We know that from here to here is R. We know from here to here is 3, right? Because the radius of the cone was 3, right? We know that the distance from here to here is 2, and we know that the distance from here to here is H. And that's about all we know. So how can we use that to somehow create a relationship? Anyone have an idea? Or I can give you a hint.
Is it like the perimeter or no?
The perimeter, is that what you're saying?
Yeah.
There might be a relationship between the perimeters of these. That would, to me, that seems like that might be a hard.
Or a right angle. I don't know. Like.
Okay, so we have a right angle. Yeah, I was gonna say, look, drop a straight line down the center, okay, like that. And let's just look at half of this thing. Just half of it. Let's just look at the right side. We would have something that looks like this. This. Right, and then we have from here over down. We know that this is R. We know that this is H. We know that this is 3. And that is 2, right? Do we agree with that? Okay. See that right angle? See that right angle? See those 2 triangles right there?
Can we do similar triangles?
Yeah, we can, because this angle here is the same as this angle here, isn't it? Because this angle is on the same line, and then this is flat and this is flat. So these 2 angles should be the same. And they should also have a 90-degree angle, which means that this angle and this angle have to be the same. And that means that the yellow triangle and the blue triangle are similar, which means that the ratio of corresponding sides must be equal. We've talked about what it means to be similar triangles, but I need to somehow figure out how I can like label these triangles. So let me draw the yellow one first. I'm gonna draw it over here. Here's my yellow one. I'll even make it yellow for you. There you go. So you know which one I'm talking about. And then my other triangle, which is, you know, over here. This is my blue one. Okay. So let's start with the yellow one. What do I know? I know this is R. And then the only other thing I know easily is that on the blue triangle, this is H. Do y'all agree with that so far? Yes. Okay, can we figure out what this side is? And can we figure out what this side is? What do you think?
Yeah,
Okay,
They're the-
how?
they're the same triangle, aren't they? So they should be equal, right?
Well, I'm just, it's like I cut this yellow one off and I put it over here, and I cut this blue one off and put it over here to here is H. I know from here to here is R. What I'm asking is, do you know this distance from here to here?
H.
H minus 2.
Oh,
Other way around, not H.
2
minus
minus H.
two, other way, 2 minus H. Right, so just imagine, what if H was 1? Then the rest of it would have to be 1 as well, right? If H was a half, then you would have to still get up to 2, right? So you would take 2 and subtract a half, that would leave you with 1.5. So this side right here with the question mark on the yellow one is 2 take away H. 2 take away H, all right? Questions on that? How about the other question mark that we're talking about, this side right here, right? That's what we're talking about. This one was this side right there.
Would it
3
be
minus
minus
3 minus r.
3 minus R, 3 minus R, because we know the whole distance from here to here is 3. So whatever R is this, right? From here to here is R, so is this. So if R was 1, then this distance would be 2, right? So you're just subtracting the R from 3. So we can replace this with 3 minus R. And now what we can do is use the property of similar triangles and set up proportions. And there's a bunch of different ways you can set these proportions up. So I'm just going to do it the way that I want to right now. And I'm just kind of pulling this out of the air. I'm going to take this side, divide by that side, and set that equal to this side divided by that side. Okay, that's just the way I'm choosing to do it. 2 minus H over R must be equal to H over 3 minus R. That's because they're similar triangles, right? They had congruent or equivalent angles inside, which means that these triangles, be careful, when you say that two triangles are similar, you're not saying that the sides are equal. You're saying that the ratio of the sides are equal, the proportion. So it's like these triangles are just scaled up or down versions of one another. They could be equal, but they don't have to be. All right, is that an equation that connects H and R together? It is, right? So we can solve that for H or for R. It's totally up to us. I think I'm going to solve it for H because in my original objective function, H is just sitting here by itself. So if I can just find out what H is, I can just stick it right there in the in that green. So to do this, I'm going to cross multiply, even though I hate saying that. I'm going to cross multiply. Like that. Okay, so I crossed. And I have to FOIL out the left-hand side. So I get 6 minus 2R minus 3H plus RH equals RH. Is that right? Okay. Do y'all see now? We're going to try and solve this for H. Do y'all see that this and this are the same and they're on opposite sides? So they're going to cancel out. If I subtract RH on both sides, it's gone. And that leaves me with 6 minus 2R minus 3H equals 0. I will move the 3H to the other side. So I'll make it a positive 3H on the right. And then I will divide everything by 3. So 2 minus 2/3 R equals H. There we go. So just to kind of like back up and think about how we did this. You had the cylinder in the cone. The cone was fixed. We're trying to maximize the volume. We need to come up with a way to get one of these variables out of here. We use the constraint that the rectangle has to live in that cone, which means that when we do the cross section, we were able to create these similar triangles and then use what we know about similar triangles to find a relationship between R and H. That H is now going to go in and get plugged in right there. Okay. So 2 minus 2/3 R goes in there. So this now becomes, my objective now becomes volume equals pi r squared times 2 minus 2/3 r. Yeah, that's right. And my volume here is now a function of one variable r. And I'm going to distribute the r squared through. Right, I can distribute the pi r squared through, sorry. Let's distribute that through. So we will get 2 pi r squared. And then when I distribute through again, I get minus 2/3 pi r cubed. Is that all right? That's just algebraically passing pi r squared through to both of those terms. Okay, I need to go to a new page. So from here to the next page, all right? All right, let's go. So here's where we are, right? This is my objective function of a single variable, and this is where you have to make your decision on which road you're going to go down. Are we going to do this on a closed interval, or is this going to be an open interval? So think about the variable here, r. Are there any restrictions? Ash? What do you got?
Closed.
Sorry?
Oh, sorry. I thought you were asking which is
Yeah.
what we do.
You
I
said closed? Okay, so if it's closed, what would the smallest value of r be?
2. Sorry, 3. So sorry.
The smallest r you could ever use for this cylinder. It would be this scenario, right? Where you just have a straight line going down like that,
Oh,
0.
yeah.
right? That would be 0, which would be ridiculous for you to do that because you're not going to get any volume out of that. But that would be an extreme 0. And then what would the largest r could be? What would be the largest r could be here? 3. Good, Aaron. 3, because that would get you to the bottom edge of the cone, right? Now you wouldn't have any height at all because if you go all the way out with your cylinder, then there's nowhere to go up because you're already at the edges. Does that make sense? But those would be extremes. So I can do this on a closed interval. My interval is going to be that r has to be between 0 and 3, or if you want, we can just go to 0, 3 like that. That's the way we've been doing it, right? So we're going to use the closed interval or closed method, right? So the closed method means we're going to find the critical numbers. We're going to take those critical numbers. We're going to plug them into
Derivative.
nope,
Original equation.
original equation, and compare that to plugging what else into the original? The 2 endpoints. Okay, so we're gonna find the critical numbers, take those, plug them into the original function, and then we're gonna take the endpoints and plug them into the original function. We're gonna compare all the answers. Hey, David, I have a question for you. Were you just on campus?
Yes.
You were? Okay, I think I saw you.
Yeah, I always see you get out like.
Okay,
no.
yeah,
Yeah.
okay. You must live relatively close then.
Yeah.
Okay, me too. Okay, yeah, I think you were sitting in your car, or else I would have said hi. All right, so I'm gonna find the critical numbers. So we need the derivative, right? So v prime of r. All right, so don't let this thing scare you with all the pi's and stuff. This is just power rule, right? This 2 comes down, that turns it into a 4 pi r. And then this 3 comes down. And when the 3 hits the 2/3, the 3's cancel. So you should just get minus 2 pi r squared. That's it. That's our derivative. So we're going to take it and we're going to set it equal to 0. We're going to figure out also where it doesn't exist. And I think I'll start with the doesn't exist. This is never going to happen because our derivative is actually a polynomial function. It's just numbers in front of r, number in front of r squared. So this is kind of like a quadratic, basically. And now setting it to 0, that should be pretty okay, I think, because I can do a GCF, right? Greatest common factor. I can pull out a 2, a pi, and an r from all terms. I get 2 minus r in here, I believe. Set each of those equal to 0. So 2 pi r equals 0. And 2 minus r equals 0. The only solution we get here is r is 0. And over here, r is 2. So we have two critical numbers. Both those critical numbers do live in our interval, right? Between 0 and 3. So we're gonna use them now. So now what I do is I'm going to compare, right? This is time to compare here. And we're going into original, right? Original. So we're going to do the original function, which is called v. We're going to go v at 0. We're going to go v at 2. That takes care of my two critical numbers. Now I need my endpoints. One of my endpoints is already 0, so I don't have to do it twice. And so really I just need to plug 3 in. All right, so the biggest value I get out of this will be my maximum, and the smallest value I get out will be my minimum, although I'm only interested in the max. So let's plug 0 in, okay? Let's plug 0 into this volume function. That's easy, right? Because you're just gonna be putting 0 squared just kills everything, you get 0. That would be that scenario where you have just a straight line coming down the middle. It's not even a cylinder, so it doesn't have any volume. And then at 3, the same thing should happen. We should get 0, but it's not as easy to see. If you plug 3 in here, let me do it. You get 2 pi times 3 squared minus 2/3 pi times 3 cubed. And so this is going to turn into 9 times 2 pi is 18 pi. And then this is 27 divided by 3 times 2 times pi, which again is 18 pi. So you get 0 here. When you plug in 2, let's see, you get 2 pi times 2 squared minus 2/3 pi times 2 cubed. This is not going to be 0. This is going to be 4 times 2, it's 8 pi, minus 2 cubed is 8, times 2 is 16 divided by 3, so 16/3 pi. And I can figure out what that is if I get a common denominator. So I can do 24/3 pi, just rewriting the 8 as 24/3, minus 16/3 pi. This is what, 8/3 pi? That is the maximum volume that I can possibly get from a cylinder inside of that cone. There's no other cylinder I could ever create that would get a volume bigger than that. So it did not ask us for the dimensions, but we could figure out what the dimensions are, because this happened when R was 2, right? R equals 2 is where we get the maximum. And if I know what R is, then I could figure out H, couldn't I? Remember, we had a formula for H. Where was it? Back in the constraint. Here we go. H is 2 minus 2/3 R. So I could figure out that H is 2 minus 2/3 times R, but R is 2. So this is 2 minus 4/3, which is 2/3. I got a common denominator in my head there. 6/3 minus 4/3, it's 2/3. So that's it. That is the best way to do it. So if I have a cone where this is 2 feet and the radius is 3 feet, then I'm going to create a cylinder inside of it that has a radius of 2 and a height of 2/3. And if I do that, that's the cylinder that's going to have the most volume possible. So I'm sure you're thinking about this going, why in the world would I ever need to know something like that? Like how to do that? This is actually used a lot in optimizing packing materials. Like when you're going to pack things together, like let's say you gotta ship some stuff across the country and it's got to go into, containers, or even think about like global transportation. You want to move product from China to here, right? Do y'all ever buy things from China? I'm kidding, right? I had an American flag the other day and it said made in China on it. It's pretty funny. So when you're packing something, right, to ship it, you got to get as much stuff in as you can in the smallest amount of space, right? You don't just want to throw it in there. You get one shot at this, it's going to take a month for it to get where it's going, right? So there are actual people who think about optimizing packing things. And so you want to get the most, you have a container and you're trying to get the most in there, and you have all these different shapes. And so you figure out how to place things in order to get the most in that package. Does that make sense? I mean, there are people who spend their time doing this sort of logistic things, Well, they'll use a computer to do it, but the problem is the same as this. We're trying to get the most volume in a fixed shape. Okay, we're going to put optimization to sleep, at least for now, because we're going to move on. All right. It's only 1:30. It feels like I've been talking like 2 hours. Okay, that's probably how y'all feel every day, right? So I'm going to move on to 4.7. 4.7 is, even though it is part of Cal 1, okay, this is a fundamental shift that we are about to make. You could argue that we are now transitioning into Cal 2, all right? And so we're going to have new definitions and new ideas, right? Let me show you the basic idea first. And then before we do a bunch of problems, I think what I'm going to do is just kind of show you a glimpse into Cal 2 in terms of what do we use this for, all right? So right now, what you've learned in Cal 1, right? What you've learned in Cal 1, one of the main ideas is that if you're given some function f of x, right, you should be able to find f prime of x, right? You should be able to find its derivative. And to do it, to take a derivative, there's a bunch of rules you need to know, right? You need to know the power rule, the product rule, the quotient rule, and the chain rule. But see, those rules are very mechanical, right? Like once you understand the formulas, everything is very mechanical. I don't know how, well, yeah, let's just leave it at that, right? It's just a procedure almost you have to follow. Yeah, it gets tricky, right? Especially when you get like product mixed with chain or chain mixed with product. It can be tricky, but there is a systematic path through the problem. So that's what Cal 1 is about, right? I mean, there's a lot of other stuff, but that's the basic heart of everything, is taking a derivative. So in Cal 2, right, this is called, this process right here is called finding, right? Finding the derivative. Cal 2, what we do, at least in the beginning, is we try and see if we can go backwards. So I'm going to give you the derivative of some function and ask you if you can find the original function it came from. That's that process of starting with the derivative and going backwards, right, is called finding the antiderivative. Antiderivative is what you get when you go backwards. So let's do an example. All right, let's do an example. And right now, I don't want you, well, yeah, I'll do it this way. I'll do it this way. Okay, so right now, I'm going to give you this. If the derivative of some function is equal to 2x, find the original function. Now, this is supposed to be an easy problem. It's our first one. All right. So can somebody tell me what f of x is?
X squared.
X squared. Do you all agree? Yes? Because the derivative of that is 2x. Is that the only answer? Can somebody give me another answer that would still be correct?
2x plus, or x squared plus 3.
X squared plus 3 would work. Why?
Because the 3 becomes 0.
Yeah, because when we take the derivative of that, x squared plus 3, the derivative of the 3 is going to go away, and you're still going to get 2x, aren't you? And couldn't I have done that for any number? Like I could have added or subtracted any number from that. So like another answer could have been this, x squared minus 5, right? That would be a legitimate answer. In fact, I could do f of x equals x squared plus any constant. So here, c is any constant. And when I say constant, I mean any number. So it could be positive or negative, it doesn't matter. Like on this one, c would be 3. Here, c is -5. This answer is what we call the general antiderivative. These are specific antiderivatives, right? X squared is an antiderivative. X squared plus 3 is an antiderivative. X squared minus 5 is an antiderivative. But x squared plus c covers all of those. Does that make sense? It covers everything you could ever come up with. So do you all see that there's an infinite number of solutions here? There's an infinite number of solutions. And when I say solutions, I really mean functions. There are an infinite number of functions that would satisfy being the antiderivative, because you could always add a constant or subtract a constant, doesn't matter. And that would work for any function, doesn't matter what it is. All right, let's do another one. How about this one? If I tell you that the derivative of some function is x squared. Can you find me the function that it came from? So you have to think, like, what do I take the derivative of to get x squared? Well, you know that it's going to have to start with x cubed. Do you all agree with that? Because when we know that when we take the derivative, the power is going to come down, isn't it? So you know right away this is going to have to be x cubed. But x cubed doesn't work because when you take the derivative of that, that 3 comes down, doesn't it? And this doesn't have a 3, which means we need to put something in front here. What should we put?
1/3.
1/3. How about that? Why don't we put 1/3 in front of that? Now it works, right? The 3 comes out, the 1/3 kills it, and you'll be left with x squared. Now I will also do plus c because that'll take care of everything. If you want to add or subtract a number from that, all of those would still be correct answers. So far, okay? Let's do another one. What if the derivative of some function is equal to the square root of x? The derivative of a function is the square root of x. Can you find what the original function is? It might help if you think about what this really means, right? This means x to the half, right? So whatever you start with, right? Whatever you start with, when you take the derivative, right? You need to end with a 1/2 up here. So what number are we going to need on our x on this one? X to what power? If we need to end at 1/2, and we remember we subtract 1 when we take the derivative, right? So what do you subtract 1 from to get a half?
1. So 3/2.
3/2, right? 3/2. 3/2. Do y'all agree that if I take 1 away from this, I get a half? So that's the correct power. Do y'all understand that? But this doesn't work yet because the first thing I would do when I take the derivative of this is bring the 3/2 out front. And I don't have a 3/2 in front of this, right? So we're going to do kind of like what we did here. We put a 1/3 out here to kill off the 3 when it comes down. Here we need to kill off the 3/2. How can I kill off the 3/2? What can I put in front?
2/3.
2/3, good. If I put a 2/3 here, now when the 3/2 comes out, 2/3 times 3/2 will go, everything goes away and you just get a 1. And then of course, don't forget, put plus c, all right? It's kind of making sense. How about this one? If I tell you that the derivative of some function is 1/the square root of x, can you find me the original function? Take a minute. I'm gonna give you a minute. I'm gonna take a poll because I want to see if people can actually get this. All right. Let me know when you've got it. Okay. Your hint is that you should probably rewrite that derivative as x to some power and then work backwards. So we got 5 people so far that have it. If you get it, I want you to try this one. Okay, it looks like mostly everybody has the first one done. So let's just run through that real quick. So the proper way to look at this is really 1 over x to the half, and then bring that up as x to the negative 1/2. Okay. And then from there, think about what f would have to be. Well, the power would have to be 1 more than that, right? That's a pattern we've established, right? 3 halves, all I did was take a half, add 1 to it. The 3 here, I took the 2, added 1. See the power 1 here? I add 1, I got the 2. So it's the opposite of what we did with the derivative, right? With the derivative, you subtracted 1. With the antiderivative, we're adding 1. So I'm going to add 1 to this. So I know that my answer should have an x negative 1. I'm doing negative 1/2 plus 1. That's going to be a half, right? So I put a half here. But because of the power rule that 1/2 is going to come out, I don't want that 1/2 there. I'm going to just need to put a 2 here. Because half of 2 is 1, and it would go away, then plus c. That is a correct answer. You could also write this. You could switch it back to a radical. How about the second one? Does this work? Does it work the same way as the one we just did? Could you rewrite this as x to the negative 1? And then say, okay, the original function then would have to be x, well, it would be x to what power? If we follow the same pattern. Add 1 to that, you get what? 0, right? Uh-oh, we've got a problem, don't we? What's x to the 0? 1, right? So this is really 1. And the derivative of 1 is 0. It's not 1 over x. Do y'all see it doesn't work here? Doesn't work. And the reason it doesn't work is because we have to remember from Cal 1, what was it that we take the derivative of and get 1 over x? What was that again?
Square root of x.
No, careful. What do we take the derivative of and we get 1 over x?
Natural log.
The natural log. So this is one that you have to know because of our experience in Cal 1. This is from Cal 1. We are still in Cal 1, but I'm just saying, like, that's a special case. When it's 1 over x, the antiderivative is natural log. Oh, sorry, I forgot to put natural log x. Sorry, natural log x. From Cal 1, we know that the derivative of natural log of x is 1 over x. So the antiderivative 1 over x is natural log plus c. Okay, questions? All right, let's do this then. Can we find a general rule? So if I tell you that the derivative of some function is equal to x to a power, can you tell me about its antiderivative? Well, it should be an X, but what about the power on our new one?
+1.
We need to add 1 to that n, right? So it's gonna be n plus 1 here, right? So whatever this power is, add 1 to it. But think about power rule. This n plus 1 is gonna come out in front, right? And we don't want it there. So we're gonna need to kill off the n plus 1. So in front, I'm gonna put a 1 over n plus 1. Multiplied in front, like that. Then say plus c. That formula should work for any power of x that we start with, any power, except if n is -1, right? So this works if n is not -1, because what happens if n is -1 in our original problem? If we have x to the -1, that's this scenario right here, isn't it? X to the -1, and we know that that's natural log. But for any other power, this rule will work. Can you all see why the -1 doesn't work? Look at this right here. If we try and do it right here, if I try and take -1 in right there, -1 plus 1 is 0, division by 0 is undefined. So this formula doesn't work when n is -1, but that's okay because we know what the answer is when it's -1, it's natural log, all right? This has a name. This is known as the power rule for antiderivatives. See, in Cal 1, you learned the power rule, right? Well, now we have a power rule to go backwards. And that's what it is. Questions? Let me show you something. Okay, let me show you something and see if you can tell me what's wrong with this. Okay. The derivative of some function is 2 over x squared. Okay, I'm telling you that. And then I have a student who gives me this is their answer. The original function is 2x over 1/3 x cubed. Okay, so what did this student do?
Just did the antiderivative of the top and the bottom.
Yeah, they did the antiderivative of the top and the bottom. So they looked first at the top. They said, what's the antiderivative of 2? Well, what do I take the derivative of to get 2? 2x, right? You all agree that derivative of 2x is equal to 2? Yes? And then they said, what's the derivative or antiderivative of x squared? And they said, oh, okay, I'm going to add 1 to the power, and I'm going to put 1 over 3. That way it kills off the 3. Do y'all see the thinking there of that student? It's wrong. The reason it's wrong is because if I asked you to take the derivative of this, right? If I say take derivative, you have to use the quotient rule, and that's not going to generate this answer. So this is wrong, all right? This is wrong. How would you do this problem? You would take this and you would rewrite it as 2x to the -2. You'd bring that x up, that x squared up first. Okay. And then what you would do is this. Do you remember I said this all semester long? When you take the derivative of something, if you have a constant in front, it comes for the ride, right? That's what I've been saying for a long time. Constants in front of functions that when you take derivative, they come for the ride. The same goes for antiderivatives. If you have constants in front and you're finding the antiderivative, they come for the ride as well. So my antiderivative here will have the 2 that comes for the ride. And then I just need to figure out what the antiderivative of that is. And I can use this rule that we just established right here. we're trying to find the antiderivative of x to the -2. So n is -2, plug -2 into this. So you should get 1 over, I'm going to go slow here, -2 plus 1, x to the -2 plus 1. Okay, that's me using that rule right there. This is 2 times, let's see, 1 over -1 is -1 times x to the -1. And that finally comes out to be -2 on top, and I'm going to drop the x and -1 back down. -2 over x plus c. That's the antiderivative. So constants will come for the ride, all right? Always, constants come for the ride. I'm going to give you another one just to look at, all right? Just to practice here. You ready? Can I go to a new screen? Okay, yes, yeah. Okay, what if I give you this? What if I give you the derivative of some function is equal to 5 times the cube root of x squared? I want you to find the original function. Let me know when you're done. 5 is a number in front, right? 5 is a number in front. Bring it along for the ride and then take care of the rest of it. If you should finish that, just do this one. It's not meant to be a trick question or anything, but I just want to make sure I cover it. So I've got 6 people done on the first one. I think I'm going to start working it out silently to see if you're getting hung up on something here. Okay, does anyone have questions? 5's coming for the ride. Identify what n is, right? N here in this problem is 2/3, and then I apply the power rule formula. So I take, 1 over n plus 1, x to the n plus 1. Yes, I do have to add 2/3 and 1 together, so I have to get a common denominator. And that's 5/3, right? So it's going to be 1 over 5/3, x to the 5/3. 1 over a fraction is the same as the reciprocal, so 3/5. The 5's cancel. I'm left with the 3, x to the 5/3 plus c. I'm done. If I wanted to, I could write it as this. If I wanted to, I don't need to, but that would also be correct. 3 times the cube root of x to the 5th power. Questions on that? How about the other one? What's the answer over here? What's f of x?
Three x plus c.
3x plus c. That's it. It's not a trick question. My whole point is, if you have a constant by itself, the antiderivative is just that constant times x plus a constant. If you have a constant attached to a function, it comes for the ride and is attached to the front. Those are different ideas. But we had the same thing when we were doing derivatives, right? Derivative of a constant by itself was 0, but when it's attached to the front of a function, it comes along for the ride. So same thing when you go backwards. So far, Cal 2 looking okay? So far? How about this one? The derivative, the derivative of some function is this: x squared plus x squared plus x cubed plus 3. I want to know what the antiderivative is. Okay, so before we do it, what we want to do is think about things when we go backwards, how they were when we went forward, right? If we had addition and subtractions between things when we were taking derivatives, you could do them individually, right? As long as there were pluses and minuses, you could take derivatives separately. Same thing goes when you go backwards. If you have multiple terms, you can do the antiderivative of each term separately, which makes this doable, right? Because you can just look at the antiderivative of each of these. So the antiderivative of that is 1/3 x cubed plus the antiderivative of that is 1/4 x to the 4th plus the antiderivative of that is 3x, and then we say plus c. If those were minuses between, we would still do the same thing with minuses. All right. So here's where we are. Okay. Right now, if I give you a constant by itself, you can tell me the antiderivative. If I give you any power of x, you can give me the antiderivative. If I add or subtract any constants or powers of x together, you can find the antiderivative going backwards. Right? That's kind of where we are. So try this one then. I don't want you to actually try it. I want you to think about it. So what if I tell you that the derivative of some function is x squared plus x cubed plus 3, all divided by x? Now I have division, right? Quotient. And we're trying to go backwards. So what do you think? Can I just do the antiderivative of the top and then divide it by the antiderivative of the bottom? Is that the way quotient worked in the forward direction? Right? Going derivative? No, right? We had the quotient rule, which sucked. Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom square. So when you go backwards, it's not going to be easy either. All right? You cannot say that the original function is 1/3 x cubed plus 1/4 x to the fourth plus 3x over 1/2 x squared. That gets you an F in Cal 2. That's what that gets you, right? This is completely wrong. But we're lucky. In this particular problem I've given you, I had to be very careful about it. You can do this problem because there is a single term in the denominator and multiple terms in the numerator. Before you even begin to talk about an antiderivative, you can split this up into x squared over x plus x cubed over x plus 3 over x, right? That algebraically is allowed because I had one term in the denominator. And then I can rewrite that as x plus x squared plus, watch how I write this, 3 times 1 over x. Now I wrote that way for a reason, as you'll see on the next step. Now I can do antiderivative, right? Because I have 3 terms. So the antiderivative of this will be 1/2 x squared plus 1/3 x cubed plus 3 is going to come for the ride. And the antiderivative of 1 over x, I've got that burned in my brain now, is natural log of x plus c. Box it up and move on. I do have good news. In Cal 2, when you're finding antiderivatives, you can always know if you're correct or not. How can you check your answer?
Find the derivative.
Take the derivative, right? If I take the derivative of this, I better get back this, right? You could do that for all these problems, right? Do this one, take the derivative, you better get back this. Take this one, take the derivative, you better get back 3, right? You can always check your answers. Now, could I have done this problem had I flipped it over? So like if I had given you this, f prime of x is x over x squared plus x cubed plus 3. Could you then find the original function using the same method? Could you split this into 3 fractions? No. Okay. And actually right now in this class, we'd be stuck. Okay. We can't do this problem. I just want to point that out because the problem I gave you before that, I made it so it would work because I knew it would split into 3 pieces. Here, you can't split it, so we need some other way of doing this. And well, go take Cal 2, okay? And then you'll see how to do that. Okay, questions? All right, so just take a step back for a second. In Cal 1, I gave you a function, right? So in Cal 1, I gave you f prime of x, and then what you did is you took the derivative of it, and that was this, right? And that was the derivative function. And what we've been doing today, just now, is I've been asking you to go backwards, and I've been telling you that's called the antiderivative, right? So it's like a reverse process. I always think about it like this. Cal 1, you're learning how to walk forward. You're learning how to walk, jog, and run forward. And in Cal 2, you have to learn how to walk backwards, jog backwards, and run backwards. And it gets harder and harder to do, to go backwards. Okay, because in Cal 1, when you're going forward, you have eyes and you can see where you're going. What I mean by eyes is you have the product rule, quotient rule, chain rule, and power rule. Those are very clear. They're very easy to see how to do them. But when you go backwards, we have no rules. Other than the rule I gave you today, there's no other rules. What we have are methods that you might try. And it gets very hard to do, all right? Antiderivatives, generally speaking, are extremely difficult. So that's the basic idea. But Cal 1, I hand you a function f, right? And I say, go find its derivative. So in Cal 2, I want to be able to hand you a function and go tell you to find the antiderivative. So we're going to start using a slightly different notation than what I just gave you today. Instead of me writing this in yellow and asking you, instead of me saying, hey, here's the derivative of something, go find f, I'm going to write it this way. I'm going to call this f. This is what's going to be given to you. And then you got to go back and get the antiderivative. But I can't call it f anymore because this is already a little f, right? So what we call the antiderivative of f is capital F of x, okay? Little f of x is the original function. And if I want to know the antiderivative of it, I will say find capital F of x. All right? So if you look at every example I've done today, if you go back now and replace this with f of x, sorry, where are my instructions? If you replace this with f of x and replace this with capital F of x, it's the same question, except your answer is capital F of x. Does that make sense? So I just want to be able to hand you a function and not call it the derivative of something. I just hand you a function, call it f of x, and say, okay, go find its antiderivative. And you'll call that capital F of x. Okay. Man. Would you like to see what we use it for? Some things that we do with antiderivatives, why they're useful? All right, so in order for me to show you why they're useful, we have to remember what the derivative was in Cal 1, right? So in Cal 1, you start with the idea of a function, right? F of x. And then the derivative, what it represented was, if you went to some point here, x, go to your function right there, there's a tangent line right there. And the slope of that tangent line is equal to the derivative at that value x, right? So geometrically in Cal 1, give me the graph of a function. The derivative would represent the slope of the tangent line at all the different various values of x, right? It gives us a way of measuring that slope. And then we use that for all sorts of things, right? To find maxes and mins and critical numbers and all that stuff. That's the gist of Cal 1. In Cal 2, we start doing some crazy shit, okay? So what we're gonna do is this. You're gonna take a function, but you're gonna start it and stop it somewhere, okay? And then I'm gonna ask you this question. If you were to drop dotted lines straight down, my question is going to be, can you tell me the area underneath that curve? The area underneath that graph. Well, that seems like an extremely difficult problem because this curve, well, it's curved, right? I mean, it's not straight lines. It's not a circle, so you can't use like an area of a circle formula. You have to be able to somehow figure out that area. Well, guess what? If this is the function f of x, you will be able to find the area. But to find the area, you're going to have to be able to find the antiderivative of it. You're going to have to be able to find the antiderivative of this function to find the area. Once you find the antiderivative, it's very simple to do. All right? So we find areas below curves. Now, why would that be important? Why would that be important? Let me give you like a physics example. Let's say this is time, and let's say this is force. So let's say you're dragging an object along the ground, right? So at every point in time, you're applying some force to move this object. You could graph the force as a function of time, right? The area underneath this, that area will represent what we call in physics the work that you've done. It will basically be this times this. Force times, oh, one of those should have been distance. It's okay. Let's just make this one distance. You apply a force over a distance, that's work, okay? So areas under curves are actually meaningful. It depends on if you're in physics or chemistry or whatever. Those things have different meanings, all right? And then we'll do some, but the key is that you need to be able to find the antiderivative to be able to answer that question, all right? The next one that I want to show you, I'm going to actually show you an animation from my Cal 2 class because I think it'll make a little more sense. Hold on, can't remember. Oh, yeah. Let me get this going here. Okay. All right, so these are two functions, right? And there is a way to use the antiderivative to find the area between those, okay? I'm telling you this, all right? If you give me two functions, I can find the area between. That's one thing we do in Cal 2. Another thing we do is this, and this is pretty trippy when you see it. You're gonna imagine that this flat sheet of paper actually lives in three-dimensional space instead of on a flat sheet of paper, okay? And then what you're going to do is you're going to take that and wrap that whole region around the x-axis like that and get this shape. And my question to you is, what is the volume of that shape? Make sense? That seems like a really hard question, right? If you can find antiderivatives, you'll be able to answer that question. Another thing I could have done is instead of doing that, I could have wrapped it around the y-axis instead. Oh, sorry, wrong one. I could have wrapped it around the y-axis instead, and I would get a different shape. Do y'all see that's a different shape than if I wrap it around the x-axis? Those two shapes have different volumes. And so I would want to know the volume of each one of them. Okay, and you can do that for any region. Then we do something like this. So a question you've never had to answer before, which is, let's say you have a curve like that from here to here. And let me see, so imagine I know you may not be able to see my camera very good, but I have a little cable here. Imagine I put that cable on top of this graph, okay? Just like put my little cable right on top of the graph and I pull it up off the page. There it is. And what I'm going to do is I'm going to straighten it out. I'm going to measure how long it is. That's called the arc length. So it's like if you were like a bug traveling along this path, you'd be telling me how far your path would be to travel from that point to that point. What would the straight line distance be if you were to straighten that curve out? Okay. All right, so there's all these other geometric applications for it. That's just to give you a little glimpse into some of the things we do in Cal 2. But you have to be able to find antiderivatives, all right, which is going to be problematic, like I said. So I want you to be able to do your homework from 4-7. Let me look at it real quick. Be quiet, dude. Annoying. Hey. Okay, so what I would like for you to do for your homework is there's some things we haven't talked about that I'm going to do next time. Let's see, 4-7. Let's stop at 12. Let's stop at 12. So don't do these for now. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. What's wrong with 10? Oh yeah, it has hyperbolic in it. 11, hyperbolic, yeah. So just those, all right. And in those problems, there's a few things that you need to be aware of that I haven't mentioned today, but I'm assuming you would know it. I'm assuming from what I've said today, you would know it. So let's see. If f of x equals cosine of x, find capital F of x. What is capital F of x? What is it? What-
Sine.
Just sine,
Sine
right?
x.
Sine of x plus c, right? Why? Because you take derivative of sine and you get cosine, right? What about this? If f of x equals sine of x, careful on this one, find capital F of x. You have to be careful.
Negative cosine x.
Negative cosine.
Yeah, negative cosine x, good, plus c. Because if you just put cosine, the derivative of cosine is negative sine. And we don't have negative sign here, right? We have positive sign. So you have to put a negative in front of this so that when you take derivative, the negative will come for the ride, and then the two negatives will be positive. So there are things like that that I expect that you would know. Like, what's the antiderivative of e to the x?
E to the x.
Itself, right? E to the x, right? Plus c. Now, let me tell you about the plus c. In my Cal 2 class in the beginning, my students might forget plus c, and I might take off a little point here. As the semester goes on, if you continue to forget plus c, I'll take off more points. Some people that teach Cal 2 might count the whole problem wrong if you forget plus c, all right? You have to remember for antiderivatives, there's always a plus c, all right? So I just want you to be aware of that. People always forget it, all right? All right, we have time. What I want to do is, you know what, I could go on and show you how this is going to get hard, but why don't I open up the floor to any questions over the exam on Thursday? Are there any problems that you'd like for me to address off of the review? Or the reviews, or whatever you want to call them?
Can we do the ones you put as bonus of 2.7?
Wait, which one?
The bonus
The bonus?
is
Oh,
the one
with
of the gas engine.
this one?
Yeah. Or is it?
I don't know
extra
if I
fast?
have enough time for this one. I can give you the basic setup. I can give you the basic setup of it. How about that? The basic setup
Yes.
is that you have. Oops. I think at this point, if you're happy, you're free to go. I won't go over anything else that's going to be tested. Just make sure that you come on Thursday, cameras, all that stuff. We don't have to go through that again, right? Just come prepared, and formula sheets, blank paper, all that. Okay. All right, so on this one, what's happening here is that they give you how fast this crank arm is turning, 300 pi revolutions per minute. And they want to know how fast the piston is moving vertically. So this piston, they want to know how fast it's moving up and down. So what you can do is you can break this down into basically a point, right? Like that. You know that this distance is 8. You know this distance is 2, right? And what you want to know is how fast this thing's moving up and down. So do you all agree that the yellow point, which is right here, the crank bearing right there, do you all agree that's not moving, right? I mean, it's rotating, but it's not moving up and down. This point is going up and down. So I'm going to call the distance from here to here x. And so what I want to know is what dx dt is. I want to know how fast x is changing with respect to time. And what I know is how fast it's spinning, right? Well, that is right here. That's this measurement of this angle theta. I'm given d theta dt is 300 pi revolutions per minute. And so you need to somehow connect x and theta together. I'm cutting out a lot of things. This is the related rate problem where you have the general picture, the instant picture. What do you want? What are you given? I'm cutting a lot of that out. But you need to come up with a formula relating the theta and the x together. And I'll give you the big hint. It's not a right triangle, okay? Because the piston, depending on where it is, this triangle that I drew is not a right triangle. So to connect x and theta together, you're going to need, drum roll, law of cosines. There's a formula called law of cosines that connects an angle of a triangle to its sides. And if you use the law of cosines, you will have an equation that you can differentiate with respect to time. This is a hard problem, okay? It's a bonus problem. Does that at least help? Okay. D theta dt, I will warn you, you have to convert d theta dt from revolutions per minute to radians per minute, because a revolution is 2 pi, right? So it's doing 300 pi, 2 pi's per minute. It's weird. I used a weird number on this. Okay, I do what you want with that. Other questions?
Sir, you said that if we wanted to confirm the answers, we can ask you not to like duel the problems, but just like to see what the final answer is. Is that
Okay.
okay?
Which
Or
one do
just-
you want to?
Let me see. Number 8, the one on the review. So like, it says do one of these from A, B, and C. I just wanted to confirm the final answers. And if I got it wrong, then
Okay, hold on. Exam 3. Oh, wait, hold on. I gotta figure out which.
I think they're the ones you just passed. And
Yeah.
they're
Yeah,
under
yeah,
eight.
no. I'm trying to figure out where my solutions would be. Exam 3, fall 21. Give me a minute. I'm gonna pause my share because I don't want to accidentally show y'all something that I shouldn't, you know. I mean, like the tests, you know what I'm saying? I'm not talking about something some other file on my computer. Okay, let me see here. Fall 20. Okay, it was the 16-foot ladder on the wall. Is that one?
Yes. Well, no. This is the train that approaches on a railroad crossing at 60 miles an hour.
Okay, hold on. What the hell is it? Fall 21. Okay, it's opening. Just give me a minute. There we go. I'm having a hard time finding this thing. Okay. Because I don't want to waste your time with me sitting here trying to find this thing, can I just not work it real fast, or I think that'll take too much time?
It might. I mean, it's okay.
Which
It's
which
not-
one is it that you're asking about?
It's
the
number
train?
8. Yeah, it has
Yeah,
3
okay.
options. The ones that you said no more than an extra credit. Like,
Okay, let's see how long this takes me. It shouldn't be too bad. I need to get to today's notes. Let me get back to where I was. Okay, I'm gonna unpause. And okay, so we're talking about this problem right here.
yes, sir.
Okay. Let's see, start the clock, 2:33. Train approaches the railroad crossing 60 miles per hour, truck traveling on the road perpendicular to the train. Okay, so you got, doesn't give you any directions. So we have an intersection, we have a truck coming, and we have a train coming. Train approaches, let's say this is the train, this is the truck. Okay, train is going 60 miles an hour this way. The truck is going 30 miles an hour this way. How fast is the distance between them closing? I'm interested in this distance between them. I'm going to call that H. At a particular moment that it's 0.1. Okay, so I have a triangle. Let's call this X. Let's call that Y. So your relationship is X squared plus Y squared is H squared. Dx dt is -60 because it's closing. Dy dt is -30 because it's shrinking. And then you want to know dH dt. That's what you want to know. You want to know it when X is the moment the train is 0.1 and Y is 0.2. And the derivative is 2x dx dt plus 2y dy dt equals 2h dh dt. And now you just plug things in. The only thing we don't know in this is what h is, but we can get h from here because we know what x and y is at the moment. Do you want me to calculate it and give you an exact answer, or
No, I just messed up where I didn't put the negative.
negative?
I don't know how
Always,
bad.
did you have them as positive?
Yes.
Okay,
Always.
so that's probably just going to change your answer in the sense that your answer should be, did you get a positive answer?
Yes, I did, sir.
Okay, so that's basically the same picture, but the truck and the train are going away from each other. That's what you
Okay.
did. So, but at that instant, it's exactly the same rate, except my answer would have been negative because it's shrinking and yours is positive because they're moving away from each other.
Gotcha.
But it's the same rate.
Understood. That makes sense.
Okay, that took 2 minutes, if that.
Thank you so much.
What else?
Could you please differentiate? This is not from the review, but it's from one homework. It's just y equals x to the cosine of x. Just to confirm
Differentiate?
something.
We want to
Yeah, I
find
think
y
it's
prime?
logarithmic or yeah.
So I take the log on both sides.
Mhm.
That allows me to pop the cosine out. Now I'm ready to differentiate. So I differentiate with respect to x on both sides. So I'll get 1 over y times dy dx. That's chain rule on the left side. Always make sure you do that. You could also put y prime here if you don't want to put dy dx. Over here, you have product rule. So negative sine x times natural log x plus 1 over x, that's derivative of natural log times cosine.
Okay.
And then you just take this side and multiply both sides here by y. Am I moving too fast? Okay, but y is not y is x to the cosine x. So that would be it right there. You don't really need to do anything else with that.
Sir, on
All
the
right.
exam, sorry. Would that be acceptable or would we have to simplify it further?
No, you just leave it like this. There's really nothing you could do. You could distribute this through, but I mean, I think the back of the book a lot of times left it like this anyway.
And
So-
when you do the left side where it's y times dy dx,
Mhm.
do we write that y over there too? I don't know why I'm.
Well, I multiplied, see, I'm trying to solve for dy dx, so I had to get rid of the 1 over y.
Oh, yeah. Right. Makes sense.
Which will happen every single time you do logarithmic differentiation. You'll always get 1 over y dy dx, and you'll always multiply both sides by y.
Yep.
Okay. Maybe have, I don't know, 2 more minutes. I did a whole related rate problem in 2 minutes, so. Why didn't
Maybe
it?
just number 5 in the review, which is find the limit of x goes to infinity, x squared parentheses to the 1 over x minus 1.
What, 1 plus 2 over x, what? No,
No, sorry. So it's gonna be outside the parentheses x squared,
okay,
and then inside the parentheses 2 to the 1 over x minus 1, and then close. Yeah.
I don't remember this one. Okay, so this goes to infinity, right? 1 over infinity goes to 0, so this piece goes to 0, and 2 to the 0 is 1. So this goes to 1 minus 1, which is 0. So you have infinity times 0. Yeah? That's bad. And anytime we have that, you want to drop one of them down. So I'm going to take the one that looks better to drop down to me, and that's the x squared. So I'm going to leave the 2 to the 1 over x minus 1 on top. And on the bottom, I have a 1 over x squared now. If I were to do the limit again right now, I would get on top 0 and on the bottom 0. You could check it, if you wanted to, let x go to infinity, that goes to 0. We kind of knew that already because we did that above. And now it's 1 over x squared, that goes to 0 as well. So you have 0 over 0. So now I can use L'Hopital. Okay, derivative of the top. You have to be real careful here because remember the derivative of a to the x is a to the x times natural log a. That's a formula we did back in the day. So the derivative of 2 to the 1 over x is 2 to the 1 over x itself times natural log 2 times, and here's the critical part, the chain rule, you have to take derivative of what's up there. Sorry, I should say what's up here. And derivative of 1 over x is negative 1 over x squared. Now I know that because 1 over x, that derivative is really x to the negative 1, right? And then do your power rule. That's all over. Now I have to take derivative of the bottom, 1 over x squared. That's the same as x to the negative 2. So when I take that derivative, I get negative 2x to the negative 3. So the bottom is negative 2 over x cubed. Make sense so far? I'm not done. I can now flip. This can come up like this, right? And become x cubed over negative 2, like that. And the negatives cancel, one of the x's cancels. So you get limit, x goes to infinity. Okay, like I said, this was gone. This negative are gone. One of the x's cancel. I'm gonna have an x out in front times 2 times to the 1 over x times natural log 2. That's where I am now. Is that okay? This all became an x. Oh, wait, I forgot the 2 on the bottom. I'm sorry. Can I just throw 1/2 out here? Sorry, I forgot that 2 down there. So all of this right here becomes x over 2. And then I just put the x out front and put the 1/2 in the back. Is that all right? Let x go to infinity again. Infinity. Okay, now notice here, 2 to the 1 over infinity. 1 over infinity is 0. 2 to the 0 is 1. So that's going to 1 then times natural log 2 times 1/2. Right? That goes to infinity. Because nothing is going to 0, right? It's just infinity times a number times a number times a number. So it just becomes infinite. Okay, it's 2:42. I've got to hit the road. I'll be back in my office at 4.
Thank you.
Thank
Bye.
you.
Have a good one.
You too.